All right, today we're going to talk about oxidation reduction reactions. It's also called redox reaction, short for read from reduction and ox from oxidation. All right, let's look at the definition first. An oxidation reduction or redox reaction is a reaction that involves the transfer of electrons. That's the key, between chemical species. Chemical species would be atoms, ions, or molecules involved in the reaction. All right, so it's about transfer of electrons. All right, so during a redox reaction, some species undergo oxidation or the loss of electrons, while others undergo reduction or gain of electrons. Now, the word here is kind of confusing because reduction normally means, to decrease, but it's actually the opposite. It's gaining electrons, right? So here's an easy acronym that you can use. Oil rig. So oxidation is loss, reduction is gain. So you can use this oil rig um, acronym to memorize the words. So obviously it's loss of electrons, right? And reduction is gain of electrons. All right, let's look at an example here. So here's an example of a reaction, of a redox reaction. Here, this is a rusting of iron, all right? Now, here, Fe, right, it's a solid. Here's Fe and oxygen. They're both, they don't have any charges right now, right? They're both neutral, right? Charge neutral. But look at what it becomes. It becomes an ionic compound, right? Before this was just a metallic solid. And this was just, right, it's a molecular gas. But it becomes an ionic compound, right? And if you look at the charge for this ionic compound, it becomes Fe3 plus and then O2 minus. So there's basically two Fe3 plus and two Fe3 plus and three O2 minus in this ionic compound. So in other words, O2 as it reacted with Fe, it took away three electrons into from the Fe solid. It gave three electrons, right? Each Fe atom gave three electrons, two, but distributed it. The electrons are distributed among three oxygen atoms. So a total of six electrons were transferred. All right. Now there is something called an oxidation number so here, like, how do we know that three electrons were transferred? How do we know that O is 2 minus? Why wasn't it FeO2 where or simply FeO where it was Fe3 plus and O3 minus? Well, that's because we'll look at oxidation number, but if we look at the atomic structure of oxygen has six valence electrons, right? So normally it can accept two in order to become a full octet. So oxygen usually accepts two electrons, right? So there are some rules that we can memorize so that we can easily remember how many electrons each atoms usually take during this redox reaction. And that's called oxidation number, right? So let's look at the definition here. An atom's oxidation number or oxidation state is the imaginary charge that the atom would have if all of the bonds to atom are completely ionic. So this is basically saying if that atom were to engage in an ionic compound, right? If it becomes an ionic compound, what does it usually, what charge would it usually have? Okay. So for oxygen, we saw that it usually become O2 minus because it has 6 valence electron, so it gains 2 more, right? Well, we can kind of guess. If you look at the periodic table, what do you think would happen for fluorine? Fluorine has 7 valence electrons, so usually during an ionic in an ionic relationship, it takes only 1 electron. So F usually becomes F minus, right? So its oxidation number would be -1. So here are some guidelines for the oxidation number. We'll look at it one by one here. An atom of a free element has an oxidation number of 0, right? For example, each Cl atom in Cl2 has an oxidation number of 0. The same is true for H atom in H2, S atom in S8. Right. So a regular atom, right? It has oxidation number of 0 because it is not in an ionic compound, right? A monatomic ion. Let's look at an ion. It has an oxidation number equal to its charge. For example, the oxidation number of Cu2 plus is +2, and the oxidation number of Br minus is -1. This is basically saying they're already ions, right? They already lost electrons or gained an electron, and usually it already fulfills their octet rule. So when they engage in ionic compound, they would just engage in ionic compound as how they are right now because they're already an ion. So their oxidation number would equal to its charge. Um, when combined with other elements, alkali metals, group 1A, always have an oxidation number of +1, while alkaline earth metals would have +2. Now we know alkali metals, 1A, is talking about this one. So these are alkali, and these are alkali earth metals. Um, they usually, group 1 usually have +1, and 2 has +2. Why do you think that is? Well, if you look at the valence electrons, all of group 1 have 1 valence electron. So all they need to do is just lose 1 in order to become a full octet, to have a full valence shell. That's why when they engage in ionic compound, they just give away their electrons. So they become +1. Well, for alkali earth, they have 2 valence electron. So that's why they would give away 2 and become +2. Okay, so far, so good. Okay, so now here's some specific guidelines for each, particular elements. For fluorine, it has oxidation number of -1. We talked about this, right? It has 7 valence electrons, so it would gain 1 electron. Now, hydrogen usually, right, has +1. It has 1 valence electron, so usually it gives away the electron, but sometimes it achieves octet by gaining an electron as well. So that exception is when hydrogen is combined with metals, such as NaH or LiAlH4. So in these cases, hydrogen gains an electron instead of giving away an electron, right? But when it's combined with non-metals, usually it would give away electrons. And that's because of electronegativity, right? Non-metals usually have very high electronegativity due to a high number of protons. Okay, how about oxygen? Like we saw it before, oxidation has an oxidation number of -2. Now, there's also an exception for this. It's in peroxides, which is compounds containing O2. So for example, H2O2 or Na2O2. In these cases, oxygen has an oxidation number of -1. So usually, right, these are the only um, examples of peroxides that would come out in AP exam. Usually it's just H2O2, but just know that, right, there are some exceptions, and it's when there are two O2 2 minus. Okay, now halogens, the other halogens. So halogens talking about group 17 right here, right? They all have 7 valence electron, right? The other halogens have an oxidation number of -1 unless it is combined with oxygen and fluorine. For example, the oxidation number of Cl in the ion ClO4 is +7. And instead of gaining 1 electron, it gives away its 7 valence electron to oxygen. Um, and that's also because of electronegativity, right? Oxygen has higher electronegativity. So since oxidation, O has an oxidation number of -2, the overall charge of the ion is -1. Right, it's because O would be -2 and there's 4 of them, so it's going to be -8. And this will be +7, so the total charge will be negative. So the sum of the oxidation numbers for all atoms in the neutral compound is equal to 0, while the sum for all atoms in a polyatomic ion is equal to charge on the ion. So this is saying basically, if you have a polyatomic ion like this, right, each O atom has an oxidation number of -2. Like we saw before, oxidation is always -2 usually. So it's going to be -2 times 3, so that's going to be -6. And what's going to be the oxidation number of N? Well, we know it has to equal -1. So since the overall charge in the ion is -1, the oxidation number of N atom must be +5. All right, let's do some examples. Assigning oxidation numbers. What is the oxidation number of each atom in these 3 cases? Right, so for SF6, we saw in the rule F has always -1 in all compounds. So since that is -1 and times 6, so that's going to be -6, right? Now we know this one doesn't have any charge, right? So it's basically charge 0. So they have to equal 0. So S must be +6. Right? Okay, how about H3PO4? Now, the rule doesn't mention anything about P yet, but we know it mentions H and O. So O, we saw that it's usually -2, and there's 4 of them. So that's going to be -8. And H, we saw that it usually has +1, right? Unless it's combined with metal. So this, since that's +1 times 3, so that's going to be +3. So this also doesn't have any charge here. So they have to equal to 0. So P is going to be +5, since they have to balance out to become 0. How about IO3 minus? Okay, in this case, we know it has to equal -1 in the end. We know that O usually has -2, and there's 3 of them. So that's going to be -6. What does I have to be? Well, I have to be, in this case, +5, right? In order to become -1. So, right. And in this case, asked us to find the oxidation number of each atom, right? So, let's go back to here. I forgot to do this. So the oxidation number of S would be +6. For F, it will be the individual oxidation number. So it's going to be -1. For here, H is going to be +1. P is going to be +5. O is -2. Right? It's not -8. We're talking about individual O. They're individually, they're -2. For here, I would be +5 and O would be -2 again, because we're talking about individual atoms. All right, I want you to do this by yourself and then check with me. So go ahead and pause the video and try to find the oxidation number. Okay, so since it has -2 on the charge, it has to equal -2. O, we know it's -2 usually. And then, so it's -6, has to equal -2. So C must be +4. So yeah, C is +4, O is -2. All right, so that's it for the first part of redox reaction. And it's about assigning oxidation numbers. All right, next time we'll look at actual reactions.